All right, well, thanks all for waking up and coming. So let me start a little bit of review of some of the things we need from last time. One thing we need is that the single particle orbitals that we're going to use are these z to some power with this exponential factor. What these look like in the plane is basically an annulus, and the radius of the annulus is magnetic length times square root of 2m. The number of flux enclosed by that ring is m equals m. And if we want the filling fraction for some quantum Hall state, what we want is the number of electrons divided by the number of flux. That's going to tell us what fraction of our lambda level is filled, because there's one orbital available for each flux that you put through the plane. So this is going to be number of electrons divided by the max power of z in the wave function, max power m, z to the m. And we can turn that around to say that the max power in a wave function is going to be the number of particles divided by the filling fraction. So for example, if we use the Laughlin wave function over here, the max power is it's m times n minus 1. Each of the other n minus 1 particles gives m powers. We're not concerned with this minus 1. So the filling fraction is n over mn, or 1 over m for the Laughlin wave function. Now the homework assignment that I gave to you all, and I'm sure you've all done already, is to show that the m equals 1 case is a Slater determinant. Slater, det. It fills all the states at nu equals 1. And one way we can write that is as an anti-symmetrized product of all the orbitals. So we'll write z1 to the 0, z2 to the 1, z3 to the 2, dot, 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 all the way up to zn to the n minus 1. And this factor a here tells you that you should switch all orderings of which one goes to which power with minus signs for each exchange. And that's what we mean by a determinant. And this thing here is proportional to the wave function we wrote down, zi minus zj. Okay? We're going to need that. Now, a bit of inspiration came to Janandra Jain, which was to take a Laughlin wave function like nu equals 1/3. Let's take nu equals 1/3 and rewrite it as psi equals product I less than j, zi minus zj squared, this factor, times another factor, product I less than j, zi minus zj. Now here, obviously, we haven't done anything. We just split up the 3 factors into 2 factors plus 1 factor. But this factor here is a determinant. And you can view this as the wave function for a single filled Landau level of non-interacting fermions. So this is non-interacting. Interacting fermions at nu equals 1. Just a Slater determinant. And this factor here, the effect of this, well, what does it do? First thing, this part of the wave function is anti-symmetric, and we want something that's overall anti-symmetric. This is symmetric, so it doesn't ruin that. If this is anti-symmetric, the whole thing will be anti-symmetric, because this is a symmetric piece. What it does is this z minus z factor, it pushes the particles away from each other. It makes the wave function vanish when they get close to each other, thereby pushing the particles farther apart from each other, thereby lowering the energy for any sort of repulsive interaction. Another way of saying this is that it's binding vortices of the wave function to the position of particles. Now, this made Jane think the following. Maybe we could generally write wave functions in the form of this product zi minus zj squared times some arbitrary wave function z1 through zn for non-interacting electrons, for non-interacting fermions, which we usually call composite fermions. They're going to be composite because they get attached to these factors. So this wave function is just going to be a single Slater determinant like you would have for non-interacting particles. And then we multiply it by this to get some sort of fractional quantum Hall state. So first thing we need to do is we need to figure out what filling fraction we're looking at. So we need to count the total number of powers of z. So the max power here that we're looking at, max power is, OK, how many powers do we have here? there's 2 times n minus 1 powers, and I'll throw away the 1. So there's 2n powers here. If you take z1, it has n minus 1 other z's, each one giving you 2. Actually, you know what? I'm going to generalize this. I'm going to do what Jane did and wrote this as 2n. We can attach any number, any even number. So this would be 2n times n. And then this part over here, well, we can write this. If this is at some arbitrary filling fraction, if we come over here, say that the max power is n over the filling fraction, this will be n divided by the filling fraction for the composite fermions from this piece. Okay? So then we want the filling fraction for this final wave function that we wrote down here. So the filling fraction for the final wave function is n over the max power, which is then n over 2nn plus n over new composite fermion. Then we'll divide through by n, multiply through by new composite fermion, and we'll get new composite fermion over 2 small n new composite fermion plus 1. Okay? So what we're going to do is we're going to do the simplest thing we can imagine doing here, which is to consider these wave functions to be some number of filled Landau levels. Like if it's 1 filled Landau level, then we get back this, which is just the nu equals 1/3 state, which we like. But suppose we put in 2 filled Landau levels instead. Well, if we put in 2 filled Landau levels, that will give us nu equals 2 divided by 2n times 2 plus 1. If we choose n equals 1, which is what we had before up here with n equals 1, this would give us 2/5. And indeed, quantum Hall states are observed at nu equals 2/5. Now, there's a little bit of a catch here, which is that we want to have a wave function which is within the lowest Landau level. And this wave function here is not in the lowest Landau level, meaning it has some z stars in it as well as z's. And we need to get rid of those. And the trick for doing that is to just modify this equation by putting a big projection operator out front of the whole thing, which basically takes all the z stars and throws them away. Just projects it down to the lowest Landau level. Now that, it's very hard to say analytically what that does, but nonetheless, that's what one does. And it generates a whole series of fractions and making a connection between integer quantum Hall effect over here and then fractional quantum Hall effect trial wave functions over here. So in particular, if we look at this series here for different integer values of new composite fermion with n equals 1 series, you'll get filling fractions nu equals 1/3, which we like, 2/5, 3/7, and so forth. And if we use negative new composite fermion, which just means we're considering the field going the other way, we then get 1, 2/3, 3/5, and so forth. And these indeed are the most, the strongest, most easily observed filling fractions in the lowest Landau level. And then if you add to these the n equals 2 series and the particle Hall conjugate of these, it basically explains 95% of all quantum Hall states that have ever been observed. Now, further than that, these trial wave functions that we wrote down here, just by guessing, they're extremely, extremely good when you compare against exact diagonalization. As good as Laughlin, 98, 99, 99.9% overlap of the trial wave function that we just wrote down as an ansatz and the exact ground state of 10 electron systems and so forth. Yeah?
When you quote a high number like that for the overlap, do you mean on some small system?
For instance,
claiming that the overlap
it will go to 0 in the infinite system size. But in the largest systems that you can actually diagonalize, which are like teens of electrons, 14, 15, that kind of number, the overlaps are still in the 98, 99%. So yes. Overlaps aren't the only indication of these things being good, but there's one indication. So anyway, this makes some connection between integer and fractional quantum Hall effect. I should have mentioned that there's another way to describe this sort of series of fractions, which is to start with, was the original way of describing it. You start with a simple Laughlin state, which we know how to describe. Then you add some electrons to it. Those electrons break up into anyons. fractionally charged anions, and then you have a bunch of anions running around, and you can make a Laughlin state out of those, condense those into an incompressible state, and that will give you the next state in the series. Then once you have that, you add some electrons, you break that up into anions, and you make a Laughlin state of that, and you condense that, and you get the next state in the series. So this is known as the hierarchy construction due to Halpern and Haldane very early on in the history of fractional quantum Hall effect. But it seems a little artificial to have this sort of successive condensation, and it seems a little bit more physical to just write down what you're interested in the first place. Now, it turns out that at least as far as topological properties, what the anion, what the quasi-particle charges are, what their braiding statistics are, what their degeneracies are on torus and so forth, all of the properties of the hierarchy states and the composite fermion states, it turns out, it's shown by Nick Reed a long time ago, that they're identical. So they're describing the same phase of matter, but here we have a very accurate wave function to describe the system as well. One thing that's also really useful about this composite fermion picture is that you can apply it not only to ground state properties, but also to excited state properties. So for example, if we're interested in nu equals 2/5 here, this is the nu composite fermion equals 2. And because we're looking at nu composite fermion equals 2, we feel that we should have the intuition that the properties of this state should be similar to that of nu equals 2 itself. So for example, nu equals 2 has 2 edge state modes, one for each Landau level, as will the nu equals 2/5 state have 2 edge state modes, one for each of these effective Landau levels. Similarly, if we draw this picture of density of states just for integer quantum Hall effect, we have a bunch of states in the lowest Landau level, we have a bunch of states in the next Landau level, and we have an empty another Landau level up here, and we go to nu equals 2, that means we fill all these, and we fill all these, and we have an incompressible state because of the gap. If we want to look at excitations of this state, the lowest energy excitations is to make a hole in this Landau level and put an electron up in this Landau level. We can take the wave function for this, which again is a Slater determinant, take this Slater determinant, stick it in here, multiply by this factor, project everything to the lowest Landau level, and it gives you extremely accurate wave functions for the excited states of the fractional quantum Hall effect at 2/5. So it then gives you intuition to try to understand what these excited states are doing as well. Okay? Questions so far? Please ask questions. Okay. No questions? All right. One thing we can also do is we can look at the limit where this thing is converging. What does that mean? It means nu composite fermion is getting larger and larger. So if we take nu composite fermion to infinity, well, what do we mean by nu composite fermion going to infinity? If you remember, the filling fraction is the density, the flux quantum divided by the magnetic field. So the filling fraction going to infinity means magnetic field going to 0. So we're thinking of a fixed number of fermions in 0 magnetic field, and that's just a Fermi C. Fermi C is where we converge to. That, if we look at the wave function we generate, so we put in a composite fermion Fermi C, just a Slater determinant of plane waves, we put that in over here, multiply by this, project to the lowest Landau level, nu composite fermion goes to infinity, and nu composite fermion going to infinity corresponds to nu going to 1/2. Okay, is that clear? Well, if we choose n equals 1, it would be 1/2n more generally. Okay. And indeed, if you look at the 1/2 state in the lowest Landau level or the 1/4 state in the lowest Landau level, it's not a quantum Hall state. It's a compressible state. It looks like a Fermi C. It appears to have a Fermi surface. You can do all sorts of experiments that you do on Fermi surfaces looking for ballistic motion of particles, and you can look at a cyclotron motion, and all sorts of experiments that you would do on a regular Fermi C. They all seem to work pretty much the same way on this composite Fermi C, even though you're in very large magnetic field. In particular, what you get is you get ballistic motion of particles over long distances, which is very surprising because you're in a very large magnetic field. And it's the fact that this effective wave function is in zero magnetic field, and somehow or other the magnetic field has been absorbed by this. So it's a rather surprising result. There have been a lot of experiments done showing that you have this Fermi C behavior at nu equals 1/2, and they seem to work extremely well. Okay, everyone still with me? Okay, so now we're going to switch here for a second, and we're going to look not at nu equals 1/2, but we're going to look at nu equals 2 plus 1/2. So now why should that be different? So 2 plus 1/2, let me just draw it over here. So we're going to fill up the lowest 2 Landau levels and then half of the next Landau level. So this one will be half populated. And in fact, strictly speaking, what we're doing here is we're filling up a spin down and a spin up Landau level, and then we're half filling the next lowest one, because actually in the real experiments you have spin. And usually, since these two are filled and there's a gap to the next state, and what we do is we just say, okay, these two are inert, let's just throw them out, because they're not going to be interesting for the low energy physics. Everything that's interesting is what's happening for this partially filled Landau level. That's very low energy physics, and we're interested in what kind of quantum Hall states or compressible states form in here. So you would think naively that nu equals 1/2 and nu equals 2 plus 1/2, otherwise known as 5/2, give you exactly the same result, but they don't. So nu equals 2 plus 1/2 is not quite equal to nu equals 1/2. We need to sort of understand why it is that they're behaving differently. Now, one of the homework assignments that I gave you, and I'm sure you've all done by now, was to work through a lot of the Landau level algebra and symmetric gauge. And one thing that you learn is that if you have a wave function in the lowest Landau level, you can generate a wave function at a higher Landau level by applying a raising operator to it. So you can just hit this with a raising operator, and you get a wave function for a partially filled higher Landau level. So this is psi higher. Okay? Now, if you're in the lowest Landau level, and we say have half-filled lowest Landau level, the thing we're trying to do, we're trying to find the ground state of some interaction. So you have some interaction or some Hamiltonian, which is basically just I less than j v of ri minus rj. And we want to find the ground state. So what we want to do is we want to minimize psi lowest Landau level, I guess v psi lowest Landau level. And if we find the ground state, if we make this thing as small as possible, you find the wave function that minimizes the energy, that gives you the ground state. If we're in a higher Landau level, we're doing a slightly different game. We want to have minimum psi higher, v psi higher, like this. And we can write the psi higher as this r operator, this raising operator, applied to the lowest Landau level. So we write it as psi lowest times this raising operator, then times the interaction, times the raising operator, times psi lowest Landau level. So you can think of the higher Landau level as being just like the lowest Landau level, except with an effective interaction, which has these raising operators attached to it. Okay? So the price we paid for working in this higher Landau level is we've modified the interaction between the electrons. Okay? So you can always treat any partially filled Landau level as being the lowest Landau level, but the price you pay is that the interaction changes somewhat. So this is why nu equals 2 plus 1/2 is not like nu equals 1/2. It's because the interaction has been modified. And actually, it's not a huge modification. It's still, the interactions look somewhat similar, but it's enough of a modification to change the physics. So what physics do you see? Well, instead of seeing a compressible Fermi liquid state, what you see is an incompressible quantum Hall state. This was quite surprising when it was discovered, because if you look at the Jane series, whose filling fractions I erased, nu equals nu composite fermion over 2n nu composite fermion plus 1. For any integer nu composite fermion, 1, 2, 3, 4, 4, whatever integer we put in here, this thing is going to have an odd denominator. So all the quantum Hall states that were observed up to that time had odd denominators. In fact, there were even papers saying that this is a theorem. You can only have odd denominator filling fractions, and then discovered an even denominator one, which was a bit surprising. So something else is going on. So I'm going to give you sort of the 0th order description of what's going on, which is what we have is a Moore-Reed wave function, a Moore-Reed Pfaffian, after Moore and Reed. I guess I should mention, Greg Moore is a very famous conformal field theorist who I think he never wrote another paper about quantum Hall effect, maybe one other paper about quantum Hall effect in his life. And he fully admits he knows nothing about quantum Hall effect, but he knows everything in the world about conformal field theory. And worked with Nick Reed, who of course knows about both. And the point of their paper was not actually to write down this wave function. The point of this paper was to introduce the methods of conformal field theory to the quantum Hall community. And this has turned out to be incredibly important for fractional quantum Hall effect. I'm not going to talk about that at all. I'm just going to write down the wave function that they happen to write down along the way as an example. So the wave function, it's going to be sort of similar to what we had before. We'll start by writing this product, I less than j, zi minus zj, we'll use squared, like this. This is a really good place to start because this is already pushing the particles away from each other, just like any composite fermion wave function, so its energy is going to be good. But this is, of course, symmetric. We need to write down a fermion wave function to turn this thing into a fermion, something that's acceptable for electrons. And what we're going to do is we're going to write an anti-symmetrized product, but instead of writing a Slater determinant, we're going to write the following. 1 over z1 minus z2, 1 over z3 minus z4, dot, 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 1 over zn minus 1 minus zn, with an assumption that n is even here. So a couple things about this. First of all, it's already anti-symmetric in 1 and 2, so you have no trouble anti-symmetrizing over these two. Then if you switch 2 and 3, you have to pick up another minus sign, so that's all hidden in here. Another thing is it may look like it's singular, like we have poles, but we don't, because every time there's a z1 minus z2 sitting here, you can just cancel a z1 minus z2 here, so it's all very well defined. The other thing is we have to look at the filling fraction we're looking at here. If we only had this term, it would be filling fraction 1/2, just like a Laughlin state. And this thing only changes the total number of powers of z by 1. So it doesn't change the filling fraction if for large n. So this is still a nu equals 1/2 wave function we're looking at. So even though this thing looks a little bit strange, and you probably haven't seen such things before, I'm going to tell you it's something you all have seen before. This is, in fact, the BCS wave function composite fermionized for a topological spinless superconductor. Now, that may not be completely obvious, but I'm going to try to make it obvious. Generally, we can write, maybe I should give the little bit of a help on the name. So the name Pfaffian comes from the following, that if you say Pfaffian of Gij, that thing is the anti-symmetrized product of G1, 2, G3, 4, dot, 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 which gives it its name. So Gij here is G of Ri minus Rj, is 1 over Zi minus Zj, like this. And this Pfaffian is actually the BCS wave function for a spinless superconductor for a fixed number of particles. Now, we never work with fixed number of particles when we do BCS theory, and there's a reason why we don't, because it's more complicated. But there are some people in the community who think that that's a mistake. And it's very easy to go off and do everything with an indefinite number of particles in your system, writing down the usual BCS wave function. But in many systems that you might actually be interested in, the number of particles is fixed. You have a block of metal. It has a fixed number of electrons. Why are you writing a wave function for an indefinite number of electrons? It seems like you're not doing the right thing. Tony Leggett has been very emphatic on this point. He says, you're obviously doing something wrong if you're not conserving the number of particles. So let me try to show how you get from the usual BCS wave function to this anti-symmetrized Pfaffian. All right, I might need some room here. So let's start with the usual BCS wave function, product over k, uk plus vk, c dagger k, c dagger minus k, applied to 0. Okay? And I'm going to divide through by the u's. So let me divide gk equals vk over uk. And this gives me product over k, 1 plus gk c dagger k, c dagger minus k, and 0. And then we can use the fact that this, although it doesn't look like it, but it can be rewritten as an exponential, e to the gk c dagger k, c dagger minus k, which is sort of a coherent state representation. So why is this OK? If you expand this exponential, the first term is 1. This is the next term. The next term will have c daggers squared in it, and c dagger squared vanishes, so you throw it out, and so forth. OK? And then this thing can be rewritten as e to the sum over k, gk c dagger k, c dagger minus k on 0. And I'm going to define this thing here to be called p dagger. OK? So p dagger, what's p dagger here? P dagger is well, OK, let's write it out again. Sum over k, gk c dagger k, c dagger minus k. This is an operator that creates a pair. If we then Fourier transform this expression from k space to real space, this thing will become integral dr1, integral dr2 of g of r1 minus r2, where this function g is the Fourier transform of this g of k, and then times psi dagger r1, psi dagger r2. Okay? So this p dagger is creating a pair of particles in the relative wave function g. So g is the shape of the orbital of the pair. Okay? Is everyone good with that? Yeah? Okay, good. So now this is our wave function is then what we have is e to the p dagger on 0, and that has an indefinite number of pairs. If we want to have a fixed number of electrons, we can just write instead p dagger, well, n over 2 pairs on 0 instead. Okay? So let's write out p dagger to the n over 2 on 0. If we do that, we'll get, well, OK, so we have for each p dagger, we have a couple of integrals. So we'll have integral dr1, dr2, all the way up to drn. Then we'll have some g's. There will be g of r1 minus r2, g of r3 minus r4, all the way up to g of rn minus 1 minus rn. And this looks a lot like this, this factor here, if these things are g. And then we have a bunch of psi daggers. Psi dagger r1, psi dagger r2, dot, 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 up to psi dagger Rn. And this thing is this piece here is antisymmetric in switching the Rs. Okay? So that means that what we're actually doing is we're creating this wave function antisymmetrized. So the BCS wave function projected to a fixed number of particles is exactly this, where we've chosen now the g of r1 minus r2 is just 1 over z1 minus z2. Okay? People happy with that? Vaguely happy with that? Incidentally, this is done on Degen's book. He works through this, or at least states the result. OK, so what we have is this thing here is a BCS wave function. And it has the property that, well, g, we can rewrite g as g of r is 1 over absolute r e to the I theta, or e to the minus I theta, I guess. And if we Fourier transform that to g of k, this gives us g of k is absolute k e to the I theta, probably with the same minus sign. And this would be a kx minus I ky superconducting order parameter. This is how we define a superconducting order parameter to be kx minus I ky. The phase of the wave function has to wrap as you go around by 2 pi. OK? All right. So once we have a BCS wave, is everyone still with me? Slow me down if I'm going too fast. Right? OK. And actually, I apologize for people who are trying to follow along in my notes. This isn't covered in my notes. Yeah. So I wrote this last night. So, OK. All right. So once we have the fact that we have a topological superconductor, that's P wave, we expect to have Majorana edge modes. We expect to have Majorana quasiparticles in Majorana zero modes in vortices. And as Charlie said yesterday, we also expect to have bosonic modes along the edge. And what I'm going to try to do now is I'm going to try to show this explicitly. The approach I'm going to use is a not often presented approach that was developed by Nick Reed and Melisa Milanovic way back in the 1990s. It's a little complicated, but I think I've managed to simplify it enough to explain how this works. And we're going to explicitly see how we get Majorana edge modes out of this wave function, I think. Let's first recall what we did for Laughlin in order to count the edge modes. So we did a couple tricks. First thing is we looked at bosons at nu equals 1/2. That made our life easier. It's, physically, it's the same thing, but it was easier to think about bosons. And then we looked at the interaction, a very simple interaction, which was a delta function, Ri minus Rj. And the reason we're using bosons at 1/2 is because we can use this delta function interaction with fermions. Delta function interactions don't do anything because they never come close to each other anyway. And the Laughlin wave function, written way over there, I guess, is exactly zero energy of this interaction because the particles never come close together. And in fact, we argued that the Laughlin wave function at nu equals 1/2 is the densest wave function, the most compact wave function you can write with the property that it's zero energy. And we said that as a function of density, or filling fraction, the energy would be 0 until we hit the Laughlin state, and then it would be finite, and then we have a cusp in the energy, and therefore a jump in the chemical potential. Therefore, we have an incompressible state. Okay? That was our first step. Our second step was to add a parabolic confinement. So we have h equals h, just the interaction part, plus some sort of parabolic confinement, alpha r squared. And we say, oh, that's really the same as plus gamma times the angular momentum operator. So looking at trying to figure out what the energies are of the low energy states in this parabolic confinement, we look for things that are still, which are basically down here where the interaction energy is 0 and the energy is just given by its angular momentum. Okay? So we listed off the angular momenta that we could have by taking our Laughlin wave function, multiplying it by symmetric polynomials. And for each unit of angular momentum, you get one unit of gamma in the energy, and that gave us our edge spectrum. This sounds familiar? Yeah? Shake your heads if no. OK. Jump up and down if not, or something. OK. OK. So what we're going to do with the Moree state is quite similar. First thing we're going to do is we're going to switch from the Moree-Pfaffian for fermions. We're going to switch to Moree-Pfaffian for bosons, erasing this factor of 2 here. Now we have an antisymmetric function times an antisymmetric function. So this thing is now a wave function for bosons, bosonic Moree. And that's just because we can work with a simpler interaction. The interaction that I claim is going to give this thing as its exact highest density ground state is actually a 3-body interaction. V naught sum of I less than j less than k, delta Ri minus Rj, delta Ri minus Rk. Okay? So what does this thing do? What this does is it allows 2 particles to come together, but it gives you a penalty if 3 particles come together. Okay? And let's look at this bosonic Moree state and ask what happens when 2 particles come together. When 2 particles come together, actually the wave function doesn't vanish. Why not? Well, if, say, particle 1 and 2 come together, well, the 0 here is going to be canceled by a pole over here, and so the wave function doesn't vanish. Now, suppose 1 and 3 came together. Well, somewhere in the antisymmetrized sum, 1 and 3 are going to have a z1 minus z3, and that part is going to not vanish. It's going to cancel the 1, 3 factor over here, and you're going to get something finite. Okay? So this wave function, it doesn't vanish when two particles come together, but you can check that it does vanish when three particles come together. How do we check that? Well, first, let's take 1 and 2 together. So 1 and 2 cancels the 1-2 factor here when they come together. But then when 3 comes in, I've already used up 1 and 2 downstairs. There's going to be 2 more factors of 0, and it will vanish quadratically no matter what I do. So when I bring 3 together, the wave function does vanish. That's roughly the argument that this is the densest thing that you can write down with that property. Okay? Everyone good with that? Okay. So in fact, we have, with this interaction, we have exactly the same physics. That energy as a function of filling fraction, it's 0 until you hit the bosonic Moore-Reed, which is actually at nu equals 1, set by this exponent, 1. And then the energy becomes finite as you try to make the density any higher. So you have a cusp, and gives you the bosonic Moore-Reed as a state, as a ground state. Okay? All right. So far, so good. Now we're going to do the same thing that we did for Laughlin, and we are going to we're going to add a confining potential. And so it's the energy. We're going to look for things that are down here that have 0 interaction energy, and that their only energy comes from the confinement, comes from the angular momentum. Yes?
Sorry, but for me it's not clear this filling fraction 1 has 0 energy.
The filling fraction, that this has 0 energy? Okay. So this will have 0. In order for this to have 0 energy, the wave function has to vanish when 3 particles come together. Yeah? Okay. And so let's just maybe write out what happens with particles 1, 2, and 3. We have z1 minus z2, z1 minus z3, z2 minus z3. And then downstairs, there'll be like a z1 minus z2, and then maybe a z3 minus z4, and dot, dot, dot. Okay? So as I bring 1 to 2, it doesn't vanish because these cancel. But as I bring in particle 3 to the same point, then in fact, there'll be 2 powers, both of which don't vanish. It actually has to vanish as an even number of powers because it's bosons, actually, and it vanishes quadratically in this case. Make sense? Good. Okay. Thank you for the question. Gold star. All right. All right. So the energy of the state, we're looking for states that are down here, and then we put them that have 0 interaction. In other words, they obey this 3-body term. They don't violate the 3-body term. But we want to give them some sort of confinement energy. So in order to find their energy compared to the ground state, we just have to see how much their angular momentum differs. So one thing we can do is we can do exactly what we did for Laughlin. We can say, let's write psi equals some symmetric polynomial times the ground state times psi bosonic Moore-Reed. Bosonic Moore-Reed. And then we can just enumerate these exactly as we did for the Laughlin state. 1 unit of angular, so we write down this these power sum I equals 1 to n, zi to the n. And then the only polynomial I can write down, which is degree 1, is just p1. And its energy is going to be just 1 unit of angular momentum, so the energy is just gamma. And we said that's really the same as the b dagger 1 on 0. And then at 2 units of angular momentum, I can write down either p1 squared, or I can write down p2. The energy, this is 2 units of angular momentum, so its energy is 2 gamma. And I could write this down as either b dagger on 0, or b2 dagger on 0, and so forth. And the effective Hamiltonian of this bosonic edge mode is gamma sum over n b dagger n bn. Okay, so this gamma is then just the edge mode velocity. N, if you think of n as being a wave vector. Okay? Everyone still happy with that? Stop me now before I Okay. All right. Can we do the same thing? So this gives us a bosonic edge mode. But in fact, that there's other edge modes we can make as well. There are other excitations we can make which will keep the property that the wave function vanishes when three particles come together and they're not of this form. Okay? So let's see if we can find what those are. So the trick here is to start breaking pairs. So we take this antisymmetric factor here. We're going to leave this factor alone. So this guy stays the same. And the antisymmetric factor, we're going to break a pair. And what we mean by that is we write we start with z3 minus z4 up to 1 over zn minus 1 minus zn. And if we try to antisymmetrize this, we get 0. Because if you try to antisymmetrize over 1 and 2, I got rid of 1 and 2. It's symmetric in 1 and 2. If you try to antisymmetrize something that's symmetric in two variables, you get 0. So that's not going to work. But it would work if I wrote z1 to the alpha, z2 to the beta, and alpha is not equal to beta. Then I can antisymmetrize again. And this will still have the property that the wave function vanishes when three particles come together. Right? I mean, the only thing this thing was doing, it was canceling one of these z1 minus z2 factors. I get rid of this thing up here, and in fact, it's going to vanish even faster. So it's still going to be 0 energy of the interaction. You're not going to get an interaction penalty for writing this down, but it will cost you some angular momentum because this is higher angular momentum than this. It gives you more positive powers of z than you have over here. So the lowest angular momentum that I could get from this, if alpha not equal to beta, is to choose alpha equals 0, beta equals 1, and that will be L equals L ground state plus 1 from 0 and 1, and then plus 1 more because I got rid of the denominator. So generally, maybe I'll just write this generally. If I write down something like this with the arbitrary alpha and beta, I have L ground state plus alpha plus beta plus 1. Clear where the 1 comes from getting rid of that denominator? Okay. All right. So then we can go on, and we can try breaking two pairs. Let me try to explain what it means to why it is that I went ahead and tried to break a pair like this. Well, this is like taking the where am I going to put this? Over here. Start erasing over here. So this is like taking the BCS wave function, or maybe I'll try to squeeze it in here. Taking the BCS wave function like this and creating a particle in orbital alpha and a particle in orbital beta. Okay? Now, when I do this, these things they're not paired, they're out of paired, they're unpaired particles that I've created on the BCS wave function. But I didn't have to say anything about breaking a pair to do this. Why not? Well, the BCS wave function has an indefinite number of particles. Here I have a definite number of particles, so in order to put things in orbitals, I had to get rid of a pair to do so. That's why I have to say break a pair and then put them in the orbitals, whereas here you have an indefinite number of particles anyway, so you just put them in the orbitals and everyone's happy. Good? So this is what I've actually done. So now let's go on and try to break two pairs. So we have this thing, same factor, antisymmetrize, and then I'm going to get rid of 3 and 4 as well, but I have to do something with the first 4 variables, z1 alpha, z2 to the beta, z3 to the gamma, z4 to the delta. And then we'll start with 1 over z5 minus z6 all the way up to the end. And again, alpha better not equal beta, not equal gamma, not equal delta. Otherwise, I can't antisymmetrize. Okay? So the effective Hamiltonian for this kind of excitation we can write out in the following way. And this is, so naturally, this thing is, C dagger alpha, C dagger beta, C dagger gamma, C dagger delta on the BCS ground state. Okay? So the Hamiltonian I'm going to write here is the following form. Will be gamma. Each time you increase the angular momentum by 1, you pay an energy cost gamma. That's the confinement energy. And then sum over n, 0 to infinity. And then I'm going to write n plus 1/2 C dagger n plus 1/2 Cn plus 1/2. So what's with this 1/2? So the reason I put in the 1/2 is because I want to account for this +1. Each time I add 2 fermions, alpha and beta, I get angular momentum alpha and angular momentum beta +1. So I'm going to assign half of that +1 to alpha and half of that +1 to beta and say, OK, let's just count up all the fermions. We'll label them by n plus 1/2, starting at 0. So the lowest energy thing I can do, if I'm making an even number of particles, is C dagger 1/2, C dagger 3/2. That's what I did here with alpha equals 0 and beta equals 1 on the BCS ground state. Okay? And since I have an even number of particles in the in my system, I always have to conserve parity, so I have to make these particles only in pairs. I can't, if I only put 1, I would then have an odd number of particles in my system, so I have to make them in pairs, even if they're not paired up. Here they're just occupying orbitals instead of being paired up. Okay? So this Hamiltonian here that we've written down is a fermionic Hamiltonian, and its spectrum is exactly what Charlie drew yesterday: 1/2, 3/2, 5/2. So this is 1/2, 3/2, 5/2. And this is a Majorana spectrum because you compare this against a Dirac spectrum. OK, we get rid of the bosons. We have to remember that they're there as well. So we compare it against a Dirac spectrum. With a Dirac spectrum, you fill up all the particles below the Fermi surface, and then you leave empty the particles above the Fermi surface. Here, there's no particles below the Fermi surface. I can't start by annihilating anyone. There's no such thing there. You can only create someone above the Fermi surface. You can't annihilate below the Fermi surface. That tells you what you have is not a fermion, but half of a fermion. You only can do half of the things that you would with a real Fermi system. So these are Majoranas. Okay? So these are the Majorana edge modes of a Moore-Reid droplet. I guess, let's see, one side comment here. So we use this, I should have mentioned earlier, we use this 3-body interaction with the bosonic Moore-Reid state. Same as with Laughlin, you can write down a 3-body interaction for the fermionic Moore-Reid state by using, instead of delta functions, appropriate derivatives of delta functions, and then integrating by parts to move the derivatives onto the wave function. It's just more complicated, but you can write down a wave function for which the fermionic Moore-Reid is the exact ground state just as well, and everything works out exactly the same. Okay. Okay. So the last thing I want to do in the remaining 10 minutes or so is I'm going to try to generalize this to look at the fermionic 0 modes of the vortices. Okay. Now the way Charlie did this yesterday is very quick. I'll repeat it. Okay, let's leave that there for a second. So you take your 2-dimensional system and you cut a hole in the middle like this. So here's your 2-dimensional system in a hole. And then you have an edge state running around the inside here. Okay? If you insert half of a flux quantum, the h/2e, through that hole, so this is like a superconducting vortex through the hole, you change the boundary condition around the edge of that hole. So instead of having excitations at energy 1/2, 3/2, 5/2, instead you get excitations at energy 0, 1, 2, 3, 0, 1, 2, 3, and this 0 is the Majorana 0 mode. It costs 0 energy, and it's half of a fermion sitting there. This sounds very convincing, but we want to see it explicitly. We want to see how this happens. In particular, one of the things we want to see is that when we have some Majorana 0 modes sitting around in our vortices, they should be qubits. We should have degrees of freedom. We should have degenerate ground states with exactly the same energy, which, for each 2 vortices, we should get one qubit. So in particular, if we add n flux, so I'll call it n flux, to the system, we expect to get 2 n vortices, because a flux is h/e, and the vortex for a superconductor is h/2e. And then for each two vortices, you have n qubits. You have 1 qubit for each 2 vortices, so this should give us n qubits, or 2 to the n states. But it's actually 2 to the n minus 1 states because there's an overall parity conservation that gets rid of half of them. Okay? So we should be able to see 2 to the n minus 1 absolutely degenerate states. Okay? So how are we going to do that? Well, we're going to try to do it by constructing the wave functions explicitly. First thing we want to do is we want to think a little bit about what the vortices should look like. So the rule for a vortex is that if you take a pair of a Cooper pair around a vortex, you should pick up a phase of 2 pi. So the way we can do that is by taking our g of r1 minus r2, which was 1 over z minus z, z1 minus z2, and changing it to g of z1, z2 equals, well, I'll write it like this, z1 minus w plus z2 minus w over z1 minus z2. As I take both of them around the position w, I'll pick up a phase of 2 pi. Okay? So then I can just take the Pfaffian, this anti-symmetrized product of these g's with the numerator, z1, z2, and that will give me a vortex at position w. Okay? Now, we're going to then try to generalize this for many vortices. And let's just, running out of space. Okay. I'm doing this terrible thing. You write something on the board and you erase it immediately. But, okay. Don't do that when you're teaching. Don't do that. Okay. All right. So I'm going to write this G, the pairing wave function, in the presence of a bunch of vortices in the following way. So I'm going to have n flux quanta added to the system, so 2n vortices. So I'm going to write z1 minus w1. So there's always going to be a z minus z in the denominator, z1 minus z2 in the denominator. But then I'll write z1 minus w1, z1 minus w2, all the way up to z1 minus wn. And then I'll start with z2s, z2 minus w1 prime, z2 dot 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 up to z2 minus wn prime. Okay? So that's all of the n vortices. And then I'm going to symmetrize over all pairings of which w goes with which z. Okay? This is going to be my g. And so I can then write a wave function. Oh, yeah, okay. One more catch of something I didn't tell you that I should have told you. Sorry about that. I only slept about 3 hours last night preparing this talk, so I apologize for being a little hectic. Okay. So the game we're going to play is the following. We want to write down wave functions on a disk with vortices on the disk. And we want to write these wave functions in such a way that the edge of the disk doesn't move. Okay? So fixing the edge of the disk to not move is that the max power of z is fixed. Okay? So I don't want to consider any excitations which are going to move the edge of the system. I only want to look at zero modes, things that involve basically excitations of the zero modes in the vortices. Okay? So that's the important piece here. Now, one wave function I can write down is, well, okay, there's always the z minus z factor, product of z minus z for bosons out front. And then I have this anti-symmetrized product of g of z1, z2, g of z3, z4, and so forth. That's one wave function I can write down. That's my first wave function. We have found one wave function that describes the vortices in these positions due to these numerators. Is everyone happy with that? Yeah.
So the position of vortices is given by the w.
So these w's are positions. So this is w1, w2, w1 prime, w2 prime, w3, w3 prime. So I'm just declaring those to be positions. And the reason I put a z minus w is because when I go all the way around it, I want to pick up a phase of 2 pi. This is the property of a superconducting vortex. When you take the pair around, you should pick up 2 pi. Okay? And they should always come in pairs, like the Sith. You know, it's more Star Wars tricks. Okay. So, so one thing we should be a little bit careful about here is how many powers of z are sitting in this factor of g. So the powers of z equal, okay, so there's 1 downstairs, and then there's, I guess, n up top. So it's n minus 1 powers. So either n factors of z, I get n factors of z minus 1, or n factors of z2 minus 1. Either one, it's n factors. Okay? So, yeah.
Where n is the number of pairs of vortices.
The number of fluxes I add, so number of pairs of vortices. That's correct, yeah. All right. So now we know, so we have one wave function we can write down, but we do exactly the same thing we do with the edge to generate those Majoranas. We break a pair. So we break a pair, and we write instead, we have this prefactor which doesn't change, and we write anti-symmetrized product of, well, okay, z1 to the alpha, z2 to the beta, and then we have g of z3, z4, up to the number of particles we have. And we know that alpha has to be not equal to beta, so not, and you know, get 0 when we anti-symmetrize. 0 should be less than alpha and beta, and should be less than n minus 1. Why should it be less than n minus 1? Well, if I go higher than n minus 1, I've increased the total number of powers of this wave function. And if I do that, I push the edge out. And my rule was I want to look for excitations that live in the bulk and not anything that's pushing the edge out. Okay? Is everyone happy with that? Yeah? Ask now if you're not happy. Okay. Down to just a few minutes. Okay, and then we can play the same game again and write break 2 pairs. So then have z1 to the alpha, z2 to the beta, z3 to the gamma, z4 to the delta, and then start with g, z5, z6, dot, dot, dot. And then we have 0. Well, none of these exponents can equal each other, and 0 is less than alpha, beta, gamma, delta, less than or equal to n minus 1. Okay? So what is it we're counting here? What we're counting is that each of these indices can take one of n possible values. So we're putting fermions in n orbitals. Okay? So if I want to count up the total number of wave functions I can write down, these are all zero energy wave functions that don't move the edge of the system. I can count them all up by, well, this is 1 here, and then it's n fermions, n orbitals choose 2 fermions. So here I put 2 fermions in n orbitals. The next one is n fermions in, 4 fermions in n orbitals. 1, 2, 3, 4 in the same number of orbitals, plus dot, 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 up till I run out of orbitals to fill. And if you sum this series, a very quick exercise in binomial coefficients, you'll get 2 to the n minus 1. So we've now written down wave functions for all of the qubit settings of our wave function, of our Moore Reed state. And these are all zero energy states of the Moore Reed special Hamiltonian. And I guess there's 2 things about this. So these are the degenerate qubit states of these zero modes. So there's 2 things that I haven't shown, which are quite hard to show. First thing that one has to show is that we have this whole bunch of wave functions which are all zero energy. What's not obvious is that they should be indistinguishable from any local measurement in the large system limit. So the statement is for topological matter that if you take one of these wave functions, you put it in a big system, you put the vortices far apart from each other, you should not be able to do any local measurement which will tell you which one of these wave functions you're in. And roughly well, okay, it's hard to see. It's in fact, it's something that's not even proven analytically, but it's been checked, and it is indeed true. The second statement is that if you take these vortices and you drag them around each other, like that, you then rotate yourself within this wave function space. One of these wave functions will turn into another, and so forth. And this gives you the non-abelian statistics of these vortices, which is also not obvious and is something that can be checked, but there's no rigorous analytic proof of it. So I think I have exactly run out of time. Maybe if there's one or two questions left, I'll take those. But thanks for your attention. Yeah.
You say that you count the vortices in chaos.
Yeah.
Which together is my 198.
Only, okay, so you can have you may or may not have a Majorana zero mode. You have a Majorana edge mode. If you have, depending on the boundary condition, meaning the number of vortices in the middle, you may or may not have a zero mode there. You could either have zero modes or half. You can either have integer modes at the edge or half integer modes on the edge. If you have an odd number of vortices in the center, then you have a zero mode at the edge, because they always come in pairs like the SIP. That you probably don't even know that reference. Never mind. Star Wars reference. If you're not a Star Wars fan, you won't know it. So they always come in pairs. So if you have an odd number of vortices in the center, then you have a zero mode on the edge as well. If you have an even number of vortices in the center, then you have half integer modes on the edge, and none of them are zero modes. Yeah. Yeah.
Which Star Wars movie is your favorite?
The first one.
Okay.
Yeah. First one meaning New Hope. Before they made all the adjustments to it, which I don't like.
Yeah, I have an actual question too.
Yeah.
Is there a limit on how many different quasi-particles can be formed from composite fermions, like besides anyons or bosons or excitons or other stuff?
How many you can make? You mean how many you can make simultaneously, or how many different varieties?
Different ones can you make?
Yeah. So they're topologically different. Different charges, different braiding statistics. Yes, there is. That the quantum Hall state sort of knows its spectrum of the different possible excitation. It's actually one of these really remarkable things about topological matter, that the ground state itself knows what kind of quasi-particles can exist. And so for the Laughlin state, you have a very limited spectrum, for example, of what kind of excitations you can make. You can have an anion of charge a third, then you can have two of those together and three of those together. And when you get 6 of them together, it's back to being an electron, and then you're done. There's no more. And for each quantum Hall state you can write down, there's some finite spectrum of topologically different charges up to addition and subtraction of an electron. Yeah.
All right. We're
Right.
already 3 minutes over, so
Okay.
unless there are any urgent questions, thanks. Good to go.
Thanks. You're next.